Let us consider the following instructive example. We need to make an asymptotic estimate for the following integral for large positive values of x. Here, mu is an arbitrary parameter. Of course, that means that t to mu is a multivalued function, and we draw the branch cut along the negative real semi-axis. The integration path is a standard Hankel contour. Now we may identify potential regions where the integral accumulates its value. First of all, these are, of course, the vicinity of the three saddle points. Here they are. And the steepest descent directions are respectively alpha is equal to pi by 4, minus pi by 12, and 7 pi by 12. And the convergence regions for the integrand are as follows. But apart from these, we now realize that we also may have the potential contribution from the vicinity of the origin. Indeed, the exponent function at t of the order of 1 over x is dominated by the first linear term. The convergence regions for the integral is the disk of radius 1 over modulus of x centered at the origin. And we basically may apply Watson's lemma for loop integrals. As you remember, we actually need to draw the contour in the steepest descent direction at the origin and sometimes spread the contour between several Riemann sheets. That is terrific. But what about the saddles? To figure out what is happening, let us again look at the steepest descent directions at the saddles and approximate convergence regions for the integrand. Here they are. Due to the steepest descent configuration, only the left saddle is accessible. Now we understand what we more or less should do. We deform the contour so it leaves the origin along the steepest descent direction. Then we have to bend the contour so it passes through the saddle, again along the steepest descent direction. Like that. Naturally, the branch cut obstructs the deformation. So we again have to interpret our complex plane as a Riemann surface containing different Riemann shades. And here is the final picture of the deformation. As you see, the contour is spread between two Riemann sheets, and the computation of the contribution from the saddle, though simple, but a little bit unpleasant. Because you need to keep track which part of the contour belongs to which sheet, keep track of the arguments of the multivalued function. So there is a small trick which allows us to avoid this complication. Instead of spreading the contour among different Riemann sheets, we bend the branch cut and the contour synchronically, like this. It allows us to stay on a single Riemann sheet and avoid splitting the contour altogether. We will use this life hack from time to time. By the way, different lectures of this course were recorded in different order, different seasons and even years, so you will notice that at some point I'll re-explain the whole trick all over again, so don't get confused. Also, if we were to find full asymptotic series, we would have to draw the exact passes of the steepest descent. Just if you are curious, here they are. Here is the initial position of the branch cut. These are the convergence regions for the integrand, and here is how we deform the branch cut and the contour along the exact steepest descent paths, if we are interested in the full asymptotic series. But since we are interested to find only the leading term, our previous simple deformation shown before suffices. Finally, let us compute the asymptotics. The first contribution comes from the branch point. It's a simple Watson's lemma. Let us make the explicit parameterization. The upper part of the contour rotates by pi by 2 clockwise and becomes t equals e to I pi by 2 times rho. The lower part of the contour rotates by the same angle and becomes t equals to e to minus 3 pi I by 2 times rho. And here we go. In the last equality, we used mirror identity for a gamma function. Next, we compute the contribution from the saddle. Fortunately, this is almost trivial. The contribution comes from two banks of the branch cut. The argument of t on the lower bank is simply minus pi. And on the upper bank is pi. The value of the exponent at the saddle is as follows. The value of the pre-exponential function at the saddle at the lower bank reads, and at the upper bank is the conjugate. Next, we recall that the steepest descent direction is pi by 4, and the contribution from the saddle follows trivially. So the full asymptotics reads. Now let's analyze the answer a little. Suppose mu is a positive integer. Then, gamma function has a pole and the first term disappears. The second term also vanishes due to the sign prefactor. So the whole asymptotic vanishes. It is to be expected. Indeed, if mu is an integer, there is no need for branch guard. The pre-exponential function is a single valued and has identical values on the lower and upper branches of the Hankel contour. The integral vanishes. Now suppose mu is negative and non-integer. Now the first term dominates over the second one, the saddle term. And you may ask the question if it is legitimate to retain the last term. To answer this question, we need to estimate the error of the asymptotic expansion of the first term, the branch point term. Indeed, if the irreducible error of the optimally summed asymptotic series coming from the branch point is larger than the saddle point contribution, it is senseless to retain the saddle term. So let's perform the necessary analysis. It's actually quite easy to build the full asymptotic series for the contribution from the branch point. We simply expand the exponential and compute the integral as an infinite sum. Each term in the sum is evaluated with the help of Watson's lemma, and we obtain the following asymptotic series. The optimal remainder term, as usual, can be estimated at the minimal expansion term as a function of k. Assuming that the optimal k is large, we use Stirling formulas for gamma function and factorials. So the modulus of the expansion term can be estimated as follows. The optimal k is easily found by the differentiation of the exponent. And the value of the optimal remainder term is as follows. So as you see, the error of the optimally summed asymptotic expansion coming from the origin is exponentially suppressed. So it is legitimate to keep the saddle point contribution in a sense that the first term is understood as implicitly representing the optimally summed asymptotic expansion. So I hope you found this discussion instructive enough. Good luck with the homework.